Hi and welcome again to my video on the energy of a chemical reaction. Today we're going to be discussing the effect of a catalyst on the energy profile of a reaction. Be it exo or endothermic reaction, we just want to explain to you what the catalyst does on the energy profile. So I'm going to quickly sketch an energy profile diagram of an exothermic reaction. So in this exothermic reaction, so we know that there is the potential energy or the energy of the system in kilojoules per mole. And then here we also have the extent of the reaction, right? So what we're going to quickly have a look at, okay, we've got substance that are going to be reacting, and then we are going to have that profile, and then you have your product, right? And then we've got your reactants. So let us say you've got substance A plus substance B coming to reacting to form your substance AB. Now, first thing we need to be able to appreciate and recognize that this type of reaction is an exothermic reaction. How do we know? We know that it is exothermic because delta HR is going to be negative. How will we know that it is negative? Well, the delta HR is calculated by saying the difference between the energy content of the product minus the energy content of the reactant. It's going to give us our delta HR. So delta HR is equal to energy of product minus the energy of the reactant, and the energy of the product is lower than the energy of the reactants, and therefore the delta HR of the system is going to be a negative, or it's going to be a value where we say delta HR is less than 0. And these obviously signify or show you that the process is an exothermic process. So this is an exothermic reaction, and we are able to conclude that. And now we also know that the activation energy of that reaction is this amount of energy, which is the difference between the activated complex minus the energy content of the reactant. This gives us our EA for the process, our activation energy. So the difference between the energy of the activated complex minus the energy content of the reactants, and this gives us our EA of the reaction. And this would be your normal or your uncatalyzed reaction. Then what happens when we bring in a catalyst? Well, what a catalyst does is that it gives the reaction an alternative pathway. It's an alternative pathway of lower activation energy. So what I'm simply saying to you is that when you introduce a catalyst into the reaction, it's going to make the reaction follow a pathway that has got a lower activation energy. So this here, the difference between its activated complex and the energy content of the reactant, this here is going to become smaller. So this is the energy profile of the catalyzed reaction, right? So what we observe is that the EA is lower than the EA of the uncatalyzed profile. So does the catalyst lower the activation energy? No, it doesn't. It gives the reaction a pathway that uses a lower activation energy. So it's important that you take note of that. It's not just taking this same reaction pathway and lowering the activation energy. It actually gives it a different pathway that is of lower activation energy. So that is your uncatalyzed reaction, catalyzed, right? And then the other one is your catalyzed reaction. So if you've got a catalyst, the reaction is going to follow a pathway of lower activation energy, and because of that, more particles are going to be able to acquire the EA that is required for them to participate in effective collisions, and therefore that is why the rate of the reaction is going to occur faster. I will in the next video talk about or show you the Boltzmann distribution of the particles in different contexts and how they speed up the rate of the reaction. If you've enjoyed this explanation, you've enjoyed this video, please like, please share, and please subscribe to our channel, and we hope to see you in the next one. All right, take care. Bye-bye.